My name is Tasneem. I'm the senior manager at 98 Percentile in the HR department. And today we did a wonderful drive with XLR. It was amazing right from the very beginning, from the very first day when I got in touch with them till today. I think it was an extremely smooth journey with them. There were multiple follow-ups done by the representatives in order to check that we would be, what time we would be coming, how many people would be coming, what vehicle we would get. To that extent, they were so precise in giving all the information to us. It was extremely great to get associated with them and have a drive at XLR campus. So we are very, very happy that we got a chance to do this. Now, coming to the students, what XLR had, I think they were extremely enthusiastic. They were well prepared. They were aware of what they are coming for. I think there was some back-end preparation which they did that was commendable. They also were very confident and they were open to any kind of thing we were asking them to do. That was I think the best part. Now, I really hope we have a very, very fruitful association with each one of them and XLR in future. We are really looking forward to have many more drives like this.
Hi everyone, my name is Prachi Sharma and I'm the Senior Project Manager for IT Department at 90th Percentile. So today we were here for this IT Bootcamp, right, this technical drive and at XLR. So it was a great experience and I would feel that the students, they are the freshers, right, but it doesn't seem like that. So if I talk about their technical and cognitive ability, they all seems pretty good in that and that's what I felt. And I guess they have been taught pretty well at XLR, so that's how they have performed good in their aptitude and the technical tests. So I wish them all the best and it was a very great experience over here.
Okay, so good morning, everyone. Let us start the session for today. So, in the yesterday's session, we were discussing about the different modeling techniques, and we checked into KNN, we checked into support vector machine, we checked into a technique called the logistic regression, and then we also checked into the bagging technique. So let us have a quick review of what are the different models we have just reviewed. So yeah, everybody, if you can kindly confirm that you can see my screen. Is my screen visible to all? Yes? Okay, great. All right. So yeah, we were checking into the different models, right? So what are the different models that we have checked? We checked into the logistic regression technique. Then we also checked into the decision tree classifier. After that, we checked into the KNN technique, and then followed by support vector machine. And then we looked into the bagging classifier, right? So we have trained these different models, and we have stored the different results in order to compare. So let me quickly run everything once. Otherwise, if I do the rest of the code, it is not going to work properly. So I need to rerun the whole code before I start changing the file. So this takes a little bit of time. Any other code before it is already executed. So pair plot generation takes a little bit of time because it is trying to map a scatter plot between every single features. So that generation of multiple scatter plots in a single graph, it takes a little bit of time. So see, it is still executing. It's about to be displayed. Have the yeah. So it took us almost a minute for the pair plot to be generated. Yeah. So the rest of the code is going to be executed in no time. As you can see, I have this. So we have three different lists maintained, right? So one is the list called M, where I'm storing the name of the models. Another is the list called TS, where I'm storing the, name, the train test split score. So we are doing the model evaluation using two techniques. Is done through two techniques. So the first one is what? The first one is the train test method. Second one is the cross validation. In our case, we are maintaining three lists. We are maintaining how many lists? We are maintaining three lists to see the model performances. Three lists to see the model performances. What is the first list? The first list is M, where I'm storing the model names. The second list is the S, where I'm storing the cross-validation score. Cross-validation score. And the third list is the TS, where I'm storing this one. Train test score. Train test model evaluation score. Now we are going to build a few more models to see whether we can get better accuracies in comparison to the already created models. So these are the already created models. Let me try to create a few more models. Okay. So what I will do now is I'm going to create another bagging classifier. Okay. I'll try another bagging classifier. So what is a bagging classifier, everyone? You remember, right? We have done it yesterday. What is a bagging classifier? Just a general idea. A bagging classifier, a bagging classifier, it takes multiple machine learning models as base models. And all the base models is the same technique. That means if you are using logistic regression as the base model, and if you want to use 100 base models, then all these 100 base models, they have to be logistic regression models. If you are taking 100 base models and you want the base models to be decision tree, then all these 100 base model is going to be decision tree classified. So this we have already built. This time, let me try and build this decision tree bagging technique. Okay, and let us see what kind of output we are going to get. So see here, I'm going to write what bagging using decision tree. So first things first, I need to initialize the bagging model. Okay, before that, I need to initialize the base model. So this time, what is my base model? My base model is going to be the decision tree classifier. Already the decision tree classifier is imported. I need to first generate the model now. So I'll just write what? BD, base decision. So it is going to be what? Decision tree classifier. And here I'm going to pass some parameters. Suppose max depth, I'm going to keep it as 3. Max depth, I'm going to keep it as 3. Okay, you can avoid this max depth also for now. That means I want the decision to be built for a full depth. But if you want, you can keep it as what? Max depth equals to 3. Now, I need to create the ensemble. That is the bagging model. So what is the bagging model? Just write bag 1. BGGL, right? Because already I think I have used bag 1. So bag 1 is equals to what? Bagging classifier. Now I have to put here what is the base model. So estimator is equals to what? Estimator is equals to, it is the BD. That is, it is the decision tree classifier. And number of estimators I want is suppose 200. Okay. Now, once this is done, I'm going to evaluate this model using cross-validation. So, cross-val evaluation. So, RES is equals to cross-val score on the model, which is bagging, on the independent feature X, dependent feature Y, and CV element in test 5. Overall accuracy is what? It is the mean of all the accuracies. And this overall accuracy, I am going to add it to the list. Just give me a minute, everyone. Sorry for this interruption. Sorry about that. So I'm going to write decision tree classifier. That means it's a bagging technique having decision tree classifier as the base. And S dot FN is what? R. So I have this now. Let me run it. For the same model, I'm also going to evaluate using the train test bit. Train test evaluation. Okay. So what I will do is I'm going to recreate the base model. So just write what dt is equals to decision tree classifier. The next step equals to 3 and PAGG1 is equals to tagging classifier. Estimator is going to be dt and number of estimators I'll keep it as 200. Now I need to apply this model to the training data. So bag1 dot fit on the X-train comma Y train. Then I need to get the prediction done on the testing data. Predict on the X test. And then I'm going to store the accuracy score into the list called TS. So let me say SC is equals to what? This is the accuracy score. Accuracy score by comparing Y test and Y red. And this accuracy score, I'll store it as what? TS dot append and SC. Enter. Now let me try to print all the strings. Print M, comma, S. Let me just write it in separate lines. Yes. Yes. So see, logistic regression, decision tree, KNN, support vector, bagging, DTC. I have this all, and these are their corresponding accuracy scores. So for bagging DTC, I'm getting fairly good result, almost 79%, but it is still lesser than the previous bagging technique which we have employed, where the base model was a logistic regression. Okay, so till now, the best model that I have received is what? Bagging classifier using the logistic regression. Okay, so this is the best one that I have yet so far. Now the next one is what? We are going to check another ensemble technique. It's called as the boosting. So for boosting, we have different boosting technique, and I'm going to be using the ADA boost technique. ADA boost. So what is a boosting technique? So what happens in a boosting technique? So what is the boosting technique? So boosting is also an ensemble technique. Boosting is also an ensemble technique, but it doesn't work the same like bagging. Bagging is a different boosting technique. Bagging is a different ensemble technique. Boosting is a different ensemble technique. What happens in boosting is you are going to have multiple base models. Okay, multiple base models. And output from one model is fed from one base model is fed to the next base model. Okay, what does this ensure? This ensures that mistakes or errors generated in previous base model is going to be corrected by the next base model. So this is the boosting technique. Okay. Errors generated in the previous base model is going to be corrected by the next base model. So under this boosting, we are going to be discussing a technique called ADA boost. So ADA boost is going to have multiple base learners. Okay, let's assume that the number of base learners ADA boost is handling is 3. It is handling three base learners. Okay, now what is going to happen? You have the data set. Okay, you have the data set. You have the set of independent features X, and you have your dependent feature 1. Now this data set is going to be fed to the first base model. It is going to be fed to the first base model. Okay, so every single row is going to be given a weight first. Every single row is going to be given a weight. And initially what is going to happen? Every single row is going to have the same weight. Suppose every single row is given a weight of 10. 10, 10, 10, 10, 10. Every single row is having a weight of 10. Now, this base model is going to work on this data, and then it is going to generate some results. Now, how accurate are the results? Suppose after this, what happened? The base model is going to get a result like this. Suppose this is Y, this is the Y predicted. And it found out that the output should have been 0, but it predicted 1. Output should have been 0, 0, 0, 0, 1, 1, 1, 1, 1, 0. So what is happening here? We have 2 mistakes done by this base model. One is this mistake, another is this mistake. Rest everything is correct. So what is going to happen? This base learner is now going to push these mistakes towards the next model. It is going to push these mistakes towards the next model. Suppose this is BM0, this is base model 1. Now, how is this base model going to identify where is the mistake done by the previous model? Because this base model, it is not going to correct the, it is not going to work on the already correct data. It has to do what? The base model is working to correct the errors, not correct the already correct data. So how is this model going to understand where is the mistake? So what happens is all these weights that you see, when this model is going to pass the data to the next model, the incorrect data, their weight is going to be increased. Suppose these were 10, now it is increased to 11. Since there was no mistake here, they are going to be kept as 10, 10, 10. And again, there was a mistake here, so this weight is also increased. Okay, so this base model is now going to see that, okay, these are the increased weight. These weights are higher. So this base model is now going to try and correct them. It is going to try and correct them. Now, it might not be able to correct all the mistakes. It might not be able to correct all the mistakes. However, overall error or overall mistakes is going to be reduced. Some corrections it is going to be able to do it, but all corrections it might not be able to do it. So what is going to happen? Remaining mistakes, it is going to forward it to the next model, base model 2. So this base model is now going to work on the remaining errors. It is going to work on the remaining errors. Okay. So on working on the remaining errors, how is it going to identify? So what is this base model going to do? Suppose this particular row was corrected. This particular row was not able to be rectified. Then what will happen? Again, the weight of this one is going to be increased. and rest everything is going to remain the same. This is going to increase. So this Bayes model will now know, okay, this is now the increased weight, which means this is the error which needs to be rectified. So again, this is going to work so that it is able to correct as much remaining error as possible. Now what happens in this model? Again, errors are reduced. So like this, multiple Bayes models will be kept, and every single Bayes model will try to minimize the error as it passes the same data forward. Okay, so this is how boosting works. This is how boosting works. Is this understood, everyone? All right. So let us now try to execute this. Now, AdaBoost as a Bayes learner is going to consider decision tree, but it is always going to have a decision tree of depth 1. That's it. Okay. It's always going to have a decision tree of depth 1 as its base. So let us try to construct this. So what will I do? For AdaBoost, I'm going to call now from sklearn dot ensemble import AdaBoost classifier. AdaBoost classifier. The next step is to create the model. So AD8 is equals to what? AdaBoost classifier. Now here I don't have to give any kind of information. I'll just take the default estimator and I'm going to just specify the number of estimators. So number of estimators, I'm going to keep it as what? I'm going to keep it as suppose 200. Okay. The next step is to evaluate this model using cross validation. So cross-val score. So how do I check it now? I have to import the cross-val score. So cross-val score on what? On the model AD8 x comma y and CV equals to 5. And put the result. Start and boost and R. So the AdaBoost technique is going to start running now. And I have this. Okay. The next thing is to use train test technique. So ADA1 is equals to specifier number of estimators to 200 strain comma y train, that is fitting the model to the training data. Now using this trained model, I need to predict on the test data. After the prediction is done, the result needs to be stored in y red. Once this is done, I need to get the accuracy score. So A equals to what? Accuracy score by comparing the actual data and the predicted data. So TS dot append A. Control Enter. And this is now executed. So what I will do, I'll try to now see the list, all the lists, and whether this data is correctly added on. So see, I have the Adabus classifier, and for the Adabus classifier, I'm getting this as what? As this. This is my cross-validation accuracy, and this is my train test accuracy. This is my train test accuracy. Okay. So this is what I have for the Adabus classifier. The next is what? The next is I'm going to try out random forest classifier. Random forest classifier. So random forest classifier is going to be the same as your bagging technique, but mandatorily random forest is always going to have a decision tree at its core. It is always going to work by having a decision tree at its core. Okay, so we are going to use the random forest classifier. So from sklearn dot ensemble import random forest classifier. The next step is to specify the features of the model by initializing. So RF is equals to what? Random forest classifier. Random forest classifier. Number of estimators. By default, it is going to be 100. You can increase it. I'll just keep it as 300. And the max depth of every decision tree should be limited to 4. And I'm going to say that maximum features, it is going to take is 3. Why is it not coming up? Yeah, max features should be 3. Okay, I'll explain to you what this max feature is about. Okay, after that, I'm going to apply cross-validation on this data. Cross-val score on the model RF. This one on Y, and CV equals to 5. After that, random forest and s dot append are executing this. So we have evaluated 8 models till now. Let me also do the train test 4. And in train test, again, the same process will be repeated. Suppose RF1 is equals to what? I'll just copy this whole thing again. And then I need to fit this model to the data. Fit on extreme comma whiting. The process is the same, repetitive process, but models are going to be different. After fitting, you need to evaluate on the testing data. So predict on X test. I'm going to store the result in what? Let me store the result. White red, and then get the accuracy. So we A equals to white test and white red. Yes, Dr. Pence. We paste all of this to see this now. And I have this. So random forest is giving me this much. Just give me a minute. I think there is some kind of a mistake happening here. Plus extrain and write remix test and the white test. Okay. So I'll do what? I'll just quickly restart and run all everything once. Yes. Now I'm getting the different accuracies. So there you have it. Okay. So this is your random forest classifier. So I'll do what? Just to avoid the reprinting of everything. Uh, Sorry, I need the reprinting of everything, but then when I'm using this pair plot, it takes a lot of time. So what I can do is, once you have evaluated your pair plot and if you want to rerun the program, then you can simply comment it out. Okay, you can simply comment it out. So if you want, you can do that. All right. So I have this random forest done. The next is what? I'm going to be using a Gaussian model. Sorry, I'm going to be using a voting classifier. Gaussian NB, I'll be using it, but first let me do the ensembles, then I will. So, what happens in ensemble? When I say ensemble techniques, I'm talking about what? When you are using multiple Bayes models, and you are constructing a full model. So this full model, full machine learning model is actually constructed by multiple Bayes learners. Multiple Bayes learners. Now, when it comes to ensemble techniques, we have actually three types of ensemble techniques. One is the begging technique. Another one is the boosting technique. And the last one is the stacking technique. Okay. Bagging technique works in parallel. Boosting works in sequential. Okay. So what happens in bagging? You have your data set. Your data set is going to be divided, and one part of the data is going to be used to train one base learner. Then the second part of the data is going to be used to train the second base learner. Then this will be used to train the third base learner. And all of these three are now going to be learning together parallelly. Okay, after that, their output is going to be combined. So if this is generating 0, this is 1, this is 1, then the final output is going to be 1. So here in bagging technique, all the base learners, they are working in parallel. One more thing is what? All the base learners, they have to be homogeneous. That means if you are using a logistic regression model, everything has to be a logistic regression model. Same goes for boosting also. In boosting also, all the base models, they are homogeneous in nature. Okay. But boosting works in the sequential pattern. Boosting works in the sequential pattern. What is sequential? You have the data. This data is going to be fed to the first base learner. Now it is going to be passing that data in a sequence. So some mistakes will be done by this, which is going to be corrected by the next base learner, and like this, it is going to continue. Say you have specified you want 4 base learners. So whatever is the output of this final base learner, that is going to be considered as the final output. Okay. So in this scenario, you are dealing with 4 different base learners who is working in sequence here. But in case of bagging, all of these base learners, they are working in parallel. Okay. So bagging technique is using homogeneous base learner. Boosting is also using homogeneous base learner. Now stacking works similar to bagging. So works in parallel, but it can have what? It can have heterogeneous base learners. That means if one of the base learner is a logistic regression model, this can be a decision tree classifier, and this can be a support vector classifier. Okay, and the output generated by the logistic regression is going to be 0. This is suppose 1, this is 1. So the final outcome is going to be 1. So let me revise the stacking part then. So stacking works how? It works in parallel. It works in parallel, and it has what? Heterogeneous base learners. It is going to have heterogeneous base learners, which means what? You have the data set. This data set is going to be given to the logistic regression model, to the support vector machine, as well as to the decision tree classifier. Now, after training, suppose you bring in unknown data point and you ask this model, what should be the output? So logistic regression produced 1, support vector produced 1, decision tree classifier produced 1 as the output. So what is the actual output? What will be the combined output? It is going to be the highest vote. Who is having the highest vote? 0 or 1. So 0 is going to be the final output. So here the outcome is based on the vote. Okay, the outcome is based on the vote. So when we're using it in Python, in order to employ stacking technique, we are going to be using the voting classifier. We are going to be using the voting classifier. So let us do that. So and I'm going to say that base models, I'll keep it as what? Decision tree. Logistic regression, and suppose support vector machine. Support vector machine. Now, the next thing is to do what? The next thing is to create this stacking model. Okay. So, from sklearn dot ensemble import routine classifier. Okay. Now, in order to employ these different base models, I need to first initialize the base model. Then I have to pass them as a list. I need to pass these three different base learners to the voting classifier as a list. So I'm going to create a list called base. This list is currently empty. Okay. Now I'm going to create the models. Suppose M1 is equals to what? It is the decision tree classifier. Okay. Then I'm saying max depth equals to 4. Now, this model I will include it to this. This model I need to include it to this list. So how will I include it? Base dot append. And I need to pass it as a tuple. I'll name it as what? dt comma m1. Okay. Then I need to create the second base model. So M2 is equals to what? It is the logistic regression model. Logistic regression model. And I'm going to say max iter is equals to 500. Now, again, this logistic regression model also I have to add it to the list. So base dot append. I write this part LR comma M2. Now I need to create the third base model. So third base model is what? Third base model is the support vector classifier. So as we see, and this model again added to the list. Base dot append SVM M3. Now I have all the three models added to this list. Now I can construct the voting classifier. So I'll just write VC is equals to what? Voting classifier. So I'm now constructing the stacking model. So voting classifier is now going to ask you for the it is going to ask you for the list of estimators, right? So what I'm going to see, estimators is nothing but it is the list called base. So I'm going to pass base. After that, I'm going to evaluate this model by using the cross-validation technique. So R is equals to what? Cross-val score. Cross-val score on the model VC, independent feature X, Y, CV equals to 5. Okay. Then I'll get the overall mean as RES dot mean M dot append in have this executed. Next, same, I will do it for train test technique. So this same part, I'll do what? I'm simply going to I'll just copy and paste it here. Okay. Now I'll apply this model. We see the fit to extreme comma wild train. And the next thing is what? I need to now do the testing. So VC dot predict on the X test. Store the result is what? YB. Then get the accuracy as well. So now print and I'll just copy paste it from the code above. And I have this. So at the very end, I can see that Botic classifier gave me somewhere around 77% of the accuracy. Okay. So the last model that we will like to evaluate is the naive Bayes classifier. So naive Bayes classifier is going to work based on the probabilistic measure. Okay. So what is the probability? So it's going to use like this. What is the probability that a set of independent feature is affecting the Y? So it works on the principle of conditional probability. Okay. So probability of Y given X. So what is this? This means that probability of Y provided that X has already happened. So that means what? Using X, what is the probability of Y? It is equals to what? P of X bar Y. This implies what? Training probability of all features times what? Probability of Y divided by probability of X. This is how we are going to use it. Okay, this is the equation that is happening in the diagram. So in order to use this, we are going to use something known as the Gaussian naive Bayes. Okay, we are going to use something known as the Gaussian naive Bayes. So from sklearn dot naive Bayes, import Gaussian naive Bayes. So initialize this model. So NB is equals to what? Gaussian naive Bayes. After that, you are going to evaluate the performance of the model using cross validation. So RES is equals to cross val score. So NB X comma Y and CV equals to 5. Just made a mistake here. It should be Y. Now store the result as what? RES dot min. So I'll just do what? M dot append naive Bayes and S dot append RES dot mean. Now same way I'm going to evaluate the train test score. So train test score is what? It is the same. So I'll just write that NB1 is equals to Gaussian NB and NB1 dot fit on the training data dot predict on the X test, store the result in YP1 and get the accuracy score. So accuracy score, I'll just directly store it as in the list G. And if I try to print everything, I have this. These are the different models. So let me do one thing. Let me organize this entire list as a proper table. So for that, I'm just going to construct a dictionary. So D is equals to what? It is going to have a key value pair. So I'm going to say models, and key is going to be M. Then here I'm going to write Crosswell score, and the key is going to be S. Then I'll write train test score, and the key is going to be TS. So this dictionary is created. Now this dictionary, I'm going to convert it into a table. So how do I do it? PD df underscore models is equals to what? PD dot data prime. So what do I want to convert? D. This is done. And now if I try to see df underscore models, these are the models that we have built. So we have compared 10 different models till now. 10 different machine learning models. And out of all these 10 different models, let me do what? Let me sort it. Sort based on the cross-val score. I want to take the best model considering the cross-validation score. Okay, so let me just do one thing. Yeah, so now I have it like this. So this is the model that I have. Okay, so I can see that the highest cross-validation score is given to me by the voting classifier. Highest cross-validation score is given to me by the voting classifier. Okay, so what I will do is I'm going to go ahead and I will use this as my final model. So who gave you the best? Best accuracy is obtained from voting classifier. So this is now going to be taken as our final model. Okay. So this is how model evaluation is done. Is this clear till here, everyone? We do one thing. Let me give this another quick run. Restart session and run all so that we remove any kind of discrepancies we might have and we'll get the final outcome. Naive Bayes. Yeah, wait, I'll explain. So it's a very simple technique. Just give me a moment. Let's just wait till it is executed. Taking a little bit of time. Let me just go ahead. So what is naive Bayes? Naive Bayes works on the concept of conditional probability. So what is conditional probability? You have something like this, right? P of A given B is equals to what? P of B given A times P of A divided by P of B. Yes or no? This is what we have. What is the meaning behind this line? What is the probability of A? Provided B is given. Provided B is given. So in our case, what do we have? We need to find out what is the probability of the dependent variable provided set of independent features is given to us. Okay, set of independent features is given to us. Okay, so you write it like this: probability of y given x is equals to what? Probability of x given y times probability of y divided by probability of x. So what is this? This part is going to be the probability of all features in the training data. In the training data. Okay, probability of all the features in the training data. What is probability of y? Probability of y is the interested outcome divided by total number of rows. What is the probability of x? It is the probability of this only. Okay, so what is the, if you're dealing with multiple independent features, probability of x1, probability of x2, like this you are going to get it. Okay, so this is what the naive Bayes classifier uses in the background. Okay, now is this understood? Yes. Okay, so that is how it is used. Okay, so yeah, so what did we obtain? We obtained that voting classifier is giving us the best accuracy. So like this, you are going to compare different models. Okay, you are going to compare different models, and you are going to deploy the model who is going to give you the best performance. You are going to deploy the model who is going to give you the best performance. Okay, but if I see in voting classifier, I am getting this much accuracy, train test accuracy is this much, but Bayesian classifier, it is giving me this much. So in our situation, in case of cross validation, every single data point is going to be going for training as well as testing. So cross validation is more powerful when it comes to evaluating the model. Okay, so that is why I'm going to decide my best model by looking into the accuracy score given to me by the cross validation technique. So what is the final model that I'm selecting? Voting classifier. Okay, so I'll share this file with everyone. You have any questions for me? Anybody has any kind of questions for me? No? Okay then. If there is no any other doubts or queries, Monday we are going to have the final deployment class. Okay. All right then. I'll show you how deployment is done in this on Monday.
Yes, thank you so much. So there was an announcement, students. Actually, tomorrow there is no session. So whatever the session is there going to do by tomorrow, that will be postponed to the Monday. So you have to join the same link on Monday, which is on 8th of July. Okay, I request all of you to join the same link on Monday at 10 a.m. in the morning. Okay, I hope you got my point, guys. Kindly confirm me on the chat. Okay, great. So, yes, guys, thank you all. We'll meet on Monday. Okay.